Chapter 2, Observational Studies. So what is the difference between an observational study and the controlled experiments we talked about in the last chapter? For one, the controlled experiments, an investigator decides who gets the treatment and who gets the placebo. In an observational study, part of a factor of an observational study is that subjects assign themselves to groups and then the investigator just kind of sit back and watch. So again, we're going to have self-selection because the subjects determine whether they get the treatment or the control. In example 7, Dr. Javaris is a researcher who studies eating disorders. She would like to know if smoking is a risk factor for anorexia. To answer this question, she asks 100 people, all suffering from anorexia, whether or not they smoke. So first, is this a controlled experiment? No, it would be an observational study. Because she's just asking questions and watching. She's not controlling anything. Number 2, what is the treatment? That would be smoking. Because we want to see if smoking causes or is a risk factor for anorexia. And finally, how are the subjects assigned to the treatment and control groups? Well, obviously, subjects are choosing whether they want to smoke or not smoke. So this would be an example of self-selection. Example 8. In 2006, Swedish researchers reported the results of a study looking at the relationship between cell phone use and brain tumors. They found a 240% greater risk of developing a brain tumor on the side of the head which an individual uses the device compared to the other side of the head. First, what is the treatment in this study? That would be cell phone use. Whether or not you use a cell phone. Was this study an observational study or a controlled experiment? For this one, there's not enough detail to tell. It's possible that they rounded up some people and they gave phones to some people to use and then the other people didn't. They didn't give them any cell phones, and if this was long enough ago, it might have been before everyone had cell phones already. But because they didn't tell me for sure what they did, it's usually a safe assumption that they didn't design the experiment well if they're not proud of how they designed the experiment and they didn't tell you how they designed the experiment. Also, it's less likely that they did find a bunch of people that didn't have cell phones to start with so that they could do this controlled experiment. And so I would guess that it was an observational study. And number 3, how could we design a controlled experiment? Now, this isn't the only way to do it. This is just one way. So I would have one group that uses cell phones. And because we're looking at which side of the head they develop a brain tumor on, I'm going to say that they can only use cell phones only on the right side of their head. And then I would have one group that can't use cell phones so that we can see if the cell phones are causing this. And if you really wanted to be thorough, you could have one group that only uses cell phones on the left side. Now, this might be very difficult to do, to actually train people to only use cell phones on the right or left side of their head. And then I would randomly assign people to each group. And because I'm randomly assigning them, that helps me get groups that are similar, because I want groups that are similar in the amount of time spent on the phone. Or maybe you could actually control that, and so you could tell people you're only allowed to spend 20 minutes on the phone or 2 hours, whatever you might want. I would want them to be similar in age and gender, maybe race, family history of cancer, etc. Again, because with a controlled experiment, if our two groups are similar in everything but the treatment, then we can actually see if the treatment is causing an effect. And finally, just as a side note, just keep in mind that sometimes studies appear to be controlled experiments even though they're not, so you do have to look at them very carefully. So let's just summarize. In a controlled experiment, the investigator assigns subjects to the treatment group or control group. Versus in the observational study, the investigators don't assign the subjects to the groups. Rather, the subjects, or some of the subjects, have a condition whose effects are being studied, and the subjects with the condition are considered the treatment group. So when we talked about the smoking and anorexia, the subjects that smoked, that was considered the condition, and the people that smoked were in the treatment group. And for a controlled experiment, a well-designed controlled experiment can show causation, so that the treatment actually implies or causes the response. But an observational study can only show association, meaning that the treatment is associated with the response. And association does not imply causation, and we're going to talk about this a lot throughout the rest of the class. So sometimes it's not ethical or possible to assign people to treatment and control groups. In this case, an observational study may be the best that we can do. So for instance, it's not ethical to assign individuals to a smoking group, as smoking is a known health risk. What we do in these situations is we do the best that we can, so we do observational studies. But for example, with smoking, they've done enough observational studies that are all showing the similar results to show then that smoking is a health risk. And finally, a little cartoon to help emphasize the point that association is not causation. So they're on the plane, and the boy says, "I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy." But what you have to keep in mind here is that turning on the seatbelt sign is associated with a bumpy flight. The two things are related. However, turning on the seatbelt sign does not cause the bumpy flight. This is a situation where we have a confounding factor. Remember, a confounding factor is something that's associated with both groups, or in this case, both instances. So the confounding factor would be turbulence. Because if it's turbulent, they're going to turn on the seatbelt sign, and if it's turbulent, it's going to be a bumpy flight. And so turbulence is confounding our relationship here because it's affecting both the seatbelt sign and the bumpy flight. In example 9, a state is evaluating a new after-school program to help keep children off the streets. The program involves several months of tutoring, sports, and other activities with very strict discipline enforced. Admission to the program is voluntary. According to the school board member, those who participate in the program regularly are less likely to get into trouble with the law at any time during their lives. First, what is the treatment? The treatment is the after-school program. Next, what is the treatment group and what is the control group? The treatment group is the kids in the program. The control is kids not in the program. And is this an observational study or a controlled experiment? Because students are deciding if they want to be in the study because they have to volunteer, then it would be self-selection, so an observational study. Next, at a recent conference on eating disorders, a research group presented data showing that individuals who undergo a stapling procedure to control their weight tend to have obese children. The researchers concluded that the parents' stomach stapling caused the obesity in their children. If you think about that, that doesn't seem quite right. So let's go through. What is the treatment? The treatment would be having your stomach stapled. Now, are there factors that are related to both having a stomach stapling procedure and having obese children? Yes. The main one being if you are obese. Because if you are obese, you are more likely to have your stomach stapled. Okay, because why would you have your stomach stapled if you weren't obese? Okay, but you are also more likely to have obese children if you are obese. So this being obese would be a confounding factor. Because being obese affects whether or not you get your stomach stapled and also affects whether or not you have obese children. Now on this one, is it an observational study or a controlled experiment? This is another example of where there isn't enough data to tell. Okay, they didn't tell how they chose if you got your stomach stapled or not. But I doubt that the researchers chose who got their stomach stapled or not. I would assume that they just went and surveyed a lot of people that did get their stomach stapled and asked if they had obese children or not. Maybe it doesn't, because it doesn't seem fair to have a group of people and tell some of them you have to go get your stomach stapled. Now, in our observational studies, a confounding factor, rather than the actual causation, may be responsible for an observed association. A confounding factor, remember, is a difference between the treatment and control groups, other than the actual treatment, that affects the response being studied. A factor in the experiment, or again, it's a confounding factor, is a factor in an experiment which is associated both with the treatment and with the response. So a very good example of this is as children's shoe size increases, so do their reading skills. Does this prove that foot growth causes reading skill to improve? Obviously, this seems like nonsense. And there is a confounding factor here, that is age. because as children get older, they get bigger feet and they can read better as they get older. So there's this nice diagram. Notice that age is affecting foot size and reading skill. However, if you take age out of the equation, then it appears that foot size might be affecting reading skill. So we keep in mind that when we're just dealing with an observational study, that you always have to look for the confounding factors, because there could always be this third factor that's really causing the relationship that you think you're seeing. So we've talked about confounding factors and why we don't like them. Well, what can we do with them? Statisticians attempt to control for confounding factors. We try to control confounding factors by comparing homogeneous or similar groups. So for example, if gender is a confounding factor, then compare two groups of the same gender. Or if you know that age is going to be messing up your study, compare two similar age groups. So for example, if you're studying smoking, you could compare male smokers aged 55 to 59 and non-smokers aged 55 to 59. And then you've taken out gender and the age. So for example 13, in a study to determine whether or not smoking is a risk factor for heart disease, what might be some factors to control for? So we're talking about smoking, so maybe you want to control for the frequency of smoking. So the number of cigarettes that you go through in a day. Maybe family history, gender, age, race, the age when you started smoking, or just how long you smoked. And the nicotine content in what you're smoking. And maybe you can think of even more. Now, an advertisement for a graphing calculator states that research shows that schools where students have a personal calculator for use outside of class and homework tend to report higher achievement. Now, I'm telling you, or they didn't give us very many details, but I'm guessing it's an observational study. Why would I think that? Well, because I'm guessing that they probably didn't assign calculators to some schools or students and not to others. And they probably really didn't ban calculators for all the students in the control group, because they probably didn't go to their houses and take away their calculators and say you're not allowed to use a calculator at home if you're not in the treatment group. Also, this one would have to be, or this one cannot be a blind study, because obviously you know if you're using a calculator or not. Okay, and are there any variables that you think should have been controlled for in conducting the research described above? So I might control for things like the math level they're in, what math class they're in, if they get outside help. So if they come to an after-school program, or if their parents help them at home, if they're in tutoring. Another one might be how often they do homework. Or maybe what type of calculator. Since not all calculators are graphing calculators, but the people that are doing this advertisement are trying to sell graphing calculators. Another variable might be their teacher, if they have a good or bad teacher, and maybe if they come from a school or a family with money, etc. This cartoon is a very good example of association versus causation. So this top one where it says correlation, let's just cross that off and say association, since that's the term that we're using at the moment. So an association would be 100% of people who breathe die. Causation would be 100% of people who don't breathe die. And the reason why is association, obviously all people die and all people breathe, so the two things are related. However, breathing does not cause you to die. Causation, though, 100% of people who don't breathe die, because if you don't breathe, you will die because I'm not breathing. So just remember there's a difference between association and causation. Next is an interesting phenomenon called Simpsons Paradox. So a study compared a new type of kidney stone treatment to the traditional methods of all open surgical procedures. The new treatment only required a small puncture. The results are below. So of the open surgical procedures, 78% were successful. Of the new treatment, 83% were successful. Based on this data, which treatment would you want? Well, it seems fairly obvious that you would want the new treatment. However, one of the researchers then examined the data a little bit closer, and he broke down the data into the small stones and the large stones categories. So of the small stones, the open surgical procedures were successful 93% of the time, and the new treatment, they were successful 87% of the time. For the large stones, the open surgical procedures were successful 73% of the time, and the new treatment was only successful 69% of the time. So this seems very strange, right? Because the open procedure seems to be more successful for both categories. So how do you go from having the open procedure being more successful for both categories, but when you combine the data, the new treatment seems more successful? This is why we call it a paradox. How do we resolve it? Well, you have to go through and look at the number of procedures that were done with the open and new treatments based on if it's a small or large stone. So if you look at this, they gave a lot of the large stones to the open surgical procedures, and they gave the small stones to the new treatment. But it turns out the large stones are much harder to treat than small stones. Patients with the large stones are more likely to not have a successful procedure, no matter which procedure is used. Now, doctors were more likely to use the open surgical procedures on patients with large stones, and so more open surgical procedures were used on the patients with the large stones. And this caused the procedures to fail, and so more of the open surgical procedures were counted as failures. Well, only because more of the open surgical procedures were on large stones. And the new treatment was mostly used on the small stones that were easy to treat, and so the new procedures were counted as successes, and it seemed like the new procedure was better. So the conclusion was that the open surgical procedures which were used on the large stones was less successful than the new treatment, but only because the new treatment was mostly used on patients with the small, easily treated stones. And so this has come up several times, and so we've given it a name. It's called Simpsons Paradox, and it's when you have an association or comparison that seems to hold for a combined group, and we combined all the data together, but it actually changes or reverses direction when the data is examined by subgroups. And so from this, we learn that overall averages or percentages can be misleading, because conclusions that seem obvious when we only look at the total combined data can become quite different when the data is examined in more detail. In summary, when you're looking at a study, ask yourself, what is the treatment? Was there a control group? And how were the subjects assigned to the treatment group? So i.e., was this a control experiment or an observational study? When you're looking at an observational study or a non-randomized controlled experiment, ask yourself, how did the subjects end up in the treatment and control groups? Are there confounding factors? And were the possible confounding factors controlled for? the reason why that's stated as it is. So I realize this might seem slightly strange when we look at the non-randomized controlled experiment, because I don't think we've specifically mentioned, but not all controlled experiments are randomized. But they should be. That's the best way to do it. So if you're looking at an observational study or a controlled experiment that wasn't randomized, ask yourself, how did the subjects end up in the two groups? Were the confounding factors, and were the confounding factors controlled for? In summary, in an observational study, subjects self-select the treatment of control group. And association does not imply causation. Just because two things are associated, it doesn't necessarily imply that one of them causes the other one. Confounding factors might be driving the actual association that you're seeing. So beware of confounding factors, and we should control for confounding factors to avoid their ill effects. But we can't control for all possible confounding factors, but we are going to control for as many as we possibly can.